Okay, hello. And my talk could be a lot more specific than the one given later. And hearing his presentation, overall presentation, I think the key point is how we're going to be integrated into the system that he is going to develop, or already actually has started to develop. Anyway, I'm talking about Post-Fugaku Projection. The subtitle is Where Will Industry Application of HPC Go in the Post-Fugaku Era? I'm not going to about anything about AI this time, because I'm a mixture of the HPC and AI may confuse you, and I'm confining myself to the HPC only. This is the outline with what I'm going to talk about this time. First of all, I'd like to define the objective of industrial applications of HPC. Secondly, I'd like to quickly introduce flow solvers fully optimized for Fugaku and also computers in the Fugaku era. Then quickly introducing you some of the milestone applications realized in the first time in the world by Fugaku. The main dish follows as Post-Fugaku Projection, where we are going to be doing, and concluding remarks, some of the advocation. First of all, let me start with the industrial application, objective of industrial application. I'm a CFD person, solving flow and acoustics. And we have wall resolved. Wall resolved means solve every entire or tiny edges on the boundary layers. Okay? And that provides you with to predict performance of a product for completely replacing test. And also identify the essential phenomena that dominates product performance. Also, we can use that uncover unexpected and also unclassified phenomena. And of course, generate accurate data set to be referenced for developing prediction models, which I'm not referring to in this particular presentation. Let me give you some of the ideas that we are going to do. We have been doing for many years. This is a towing tank test. The test section is 400 meters. To test one ship, it costs about 20 million yen, and also a week or so. And this is a comparison of the test and predictions by the CFD. You may see scattered data predicted by the CFD. The scattering of the data predicted by the CFD does matters. It cannot be used for a completely replacement method. So we instead of relying on the model or Travis model, we have been trying to resolve everything we need to do until very tiny edges, like 500 micrometers around the 7-meter long ship. Okay? For doing that, we have developed four flow solvers because no software is available to meet our goals. The first solver is called Frontwall Blue. This is some of the target software that Professor Aoki mentioned in his talk. And also, we are developing lateral Boltzmann method. The name of the code is Frontwall X. Let me give you a quick view of the code. This is a finite element-based code. And this can provide you the ability to handle like tens of billions of grids, not tens of millions of grids that industry are commonly doing. Okay. This is a lattice Boltzmann method. The number of grids reaches to a trillion, 10 to the 12. This is the automobile aerodynamics as well as aeroacoustic applications. On the left-hand side, you have acoustic noise generated and predicted by this code. Let me quickly remind you of what we have done. We did in 5-6 years ago, like 2020, as Fugaku started its operations. We have done several things to optimize our code. The first thing we did is reordering, because if the data is scattered in the memory, you cannot expect any high performance. I think all of you know that this kind of code is upper bounded primarily by the memory throughput, not arithmetic. The second thing is to make the full advantage of the 512-bit SVE. We have completely changed our kernels, the hot kernels. The FFB is composed of 4 hot kernels, and the result is as follows. Only by changing the kernel, we have obtained 4-5 times increase in our performance. Of course, excluding the hardware performance improvement, okay? The memory throughput, as I mentioned, is very, very important. So all the time we are comparing the maximum possible memory throughut, sustained memory throughput by referring to the data taken for the Slim Triad benchmark. And we have, as I mentioned, we have 4 kernels, and out of the 4 kernels, 3 of the kernels are memory throughput bounded. And for all of the kernels, we have reached almost maximum performance that the memories can deliver us. The left-hand side kernel is not memory throughput bounded, but performance is the highest, as you are seeing. This is the performance, okay? Single node performance of each of the kernels. This, by the way, as I mentioned, was done 5-6 years ago. I'm just like to remind you of the things that we did 5 years ago, because this is very important for the things we have to do in the coming 5 years or so. A milestone achievement realized by Fugaku. The first thing is replacing towing tank tests, achieving a real numerical towing tank test. In this particular simulation, we have used about 50 billion grids. But we can do that. We could do that in the first time in the world because Fugaku has delivers us very high performance, FP64 vector operation performance, and also the memory throughput. The star area, this is an unexpected, unclarified phenomena. We haven't expected before doing this kind of simulation that the vertical structure, vertical shedding is taking place in the stamp pad. We're currently investigating this, why this happens, and what influence that this vertical structure gives on the performance, overall performance of the ship. The final slides. So this is the kind of simulation we have done by the power of Fugaku. Of course, the quantitative accuracy is very important. In this case, two lines, we have 2 lines. That is from tests. And symbols are coming from the simulations. We have 2 sets of data to compare with. And for each of the set, we have achieved a very accurate or even more accurate prediction. Even more than the tests provide us. Because tests also contains uncertainties. In the ship hydrodynamics, the free surface prediction is also important, and we are doing that. and also interaction between propeller and hull boundary layer important. Doing that as well. Okay. The next example is a numerical wind tunnel test for automobile aeroacoustics as well as aerodynamics. Let me tell you something. To producing one test car, it costs about 300 million yen. For acoustics, it costs about only 20,000 million yen for aerodynamics, because for the acoustic, you have to produce entire test cars. Clay model doesn't work. Okay? Now we are doing that by the lattice-boson method. The grade that we have used for this particular simulation is about 0.6 trillion or 600 billion. And this is acoustic waves generated around the car. In this case, particularly the APR and the side mirror produces large noise. Comparison between wind tunnel test, the spectrum, sound spectrum, predicted and produced on the right. Finally, some example of the turbo machinery. I'm going to skip some of the slides. Just one thing, we are using for this simulation like 15 to maximum 18 billion grays. Turbo machinery application are a bit more complex because you have to deal with moving interface between rotating impeller and stationary vanes. Okay? This is a comparison of the overall performance, and satisfactory result has been given. The objective is not only to predict or to replace the test, but also to identify the location where biggest loss is being produced. And this is a dissipation function, visualized instantaneously. You could never do that before Fugaku appeared. Okay. We have identified the main cause of the loss, and also the unstable phenomena, like we call rotating stall, has also been well predicted by the simulation. Okay. This is just introductory, and my main talk is post-Fugaku projection. FugakuNEXT. First of all, let me start with the general performance shift. Feasibility study completed in the last fiscal year, and now we are on the transition from Fugaku to FugakuNEXT era. He didn't mention the numbers. He only mentioned architecture. I somehow know the numbers, but not exactly. I'm not giving the exact number, but at least computer node evolution driven by unprecedented GPU capabilities, like the third next generation of GPU. Provide you, I'm just predicting, I'm not committing, maybe 220 teraflops per GPU. Okay? And also accompanied with the memory throughput delivered by the HBM6 and memory capacity as well. Every HPC performance would be at least 100 times faster or bigger in the post-Fugaku era. This is a computer node. So 100 times performance is delivered in terms of FP64 vector performance. As an industrial user, we do not care about how many nodes are composed FugakuNEXT, okay? I'm only concerned with what a single node can do and how much is that, okay? And how many nodes we need to accomplish any particular objective in industries. So 100 times the increase in the FP64 performance indicates that the benchmark test you have seen and I have shown you required about like 10 to 40,000 nodes. But if your application as well increase by its speed by 100 times, it would only requires 100 to 400, okay? That is a feasible number that industry can afford. 10,000 or 40,000 node is not a feasible number, but 100 or 400 is within a feasible number. Connections, that is done by the scale-out network. But scale-out network is not as fast as the memory throughput, okay? Increases. So I expect or I project a maximum of 100 computer nodes. That means 400 GPUs will probably hopefully connected by high-speed link, the successor of the NVLink 72. So that means 400 GPUs will be connected by high-speed links. So what this implies, it's not even weak scaled for the entire compute node. So we have to give up the idea of using a whole entire system composed of, I don't know how many, but maybe 3,400 or so. That means no longer toward a higher range number with well-resolved areas. But on the contrary, on the other hand, as I just mentioned, a very high FP64 HPC performance will be delivered with a single node. So it's time to deploy practical application or practical use of HPC and/or the real-time simulation will be possible. So this is the hope, okay? But there are many challenges to achieve this hope or to realize this hope. The paradigm shift is what you have to consider. Some of the person questioned about architecture of Fugaku and FugakuNEXT. This summarizes the architecture. Fugaku is composed of FP64, A64FF computer developed by Fujitsu. Architecture is, of course, CPU-centric, CMG core memory group based. The vector parallelism is only in the 12-bit SBE. That means only 8, okay? Multiplied by the outer thread, but number of threads is just number of core per CMG. That is only 12, okay? If you multiply 8 times 12 only gives you 96. So strategy is out of order execution and software pipelining. FugakuNEXT is, of course, GPU-centric. Architecture is throughput-oriented, GB200 successor, okay? The CUDA core count, I'm projecting, I'm not committed. The CUDA core count projected to be more than 100,000, okay? That means you have to produce more than 400 threads to store the streamlining multiprocessors to feed sufficient data to the registers. The strategy is a massive occupancy and hardware multi-threading. So at the bottom line, the inner loop parallelism must increase by orders, not a single order, by orders, from 96 to 400,000. So software development challenges, I think everybody knows that GPU prefers the simple arithmetic. So you have to navigate your code to simple arithmetic architecture or to fit with that architecture. So instruction granularity, as I mentioned, GPU favors simple arithmetic like multiplication and addition. So complex, heavy lifting, as you did in the CPU, result in a bunch of loss of time. The branch divergence it also has to be avoided. 4,000 threads must remain synchronized. The complex boundary condition in the CFD doesn't matter. You can produce, or I can produce 400 threads within the kernel. It's not a big deal, but the boundary condition implementation doesn't matter. The memory locality, coalescence access is mandatory to feed the massive core account or to fulfill the registers. Okay. Then I'm conclude. The post-Fugaku projection, I'm a bit late or fast? I don't know. A drastic and unprecedented change is likely to occur within 5 years. HPC AI computer node will split in 3 distinct classes, what I'm not mentioned in this talk, but I think this would be a bit general too. The CPU, general purpose, data intensive computing. The GPU would deliver into 2 classes. One GPU class is AI dedicated, optimized for language model, development and inferring. The GPU class 2 is just the GPU of FugakuNEXT. HPC oriented, the high-speed FP64 vector processors, and also equipped with high memory bandwidth, like HBM6, probably, and interconnect, the successor of NVLink 72, maybe up to 100 computing nodes, or 400 GPUs will be hopefully connected by the high-speed link. Application software diverges into 3 main sectors as well. The ISV software primarily run on the CPU architectures. Because it's not easy to port legacy code to the GPUs, as you may have understood. Open source software probably run both on CPU and GPU as well. The national project software is tuned, or we have to tune for the GPU. So anyway, we have to be prepared for this transition or transformation well in advance, because FugakuNEXT is expected to start its service within 5 years. We only have 4 or 5 years to go. So finally, I like to advocating for a robust code design approach. The software is not a simple matter of GPU porting of software. As I just mentioned, we need a lot deeper strategies. I'm not going into detail because I have already mentioned that. Just concluding, the hardware is poised 400 times faster in terms of its FP64 performance, and we have to catch up. The software has to catch up And for doing that, we definitely need a much more stronger collaborations. That is why I mentioned, referring to his talk, the real issue is how we're going to be integrated into his system that he is going to develop, or actually started to develop. Final acknowledgement. Of course, next for supporting many years, more than 20 years, I have done several national projects. And Fujitsu Limited, I like to quite thankful their support for particularly optimizing FAB to A64FX. A special thanks should go to Dr. Naruse of NVIDIA. He ported FAB on NVIDIA A100 GPU, maybe within a couple of days or so. But next time, it's not so easy, I think. And also Dr. Isobe and Kato for NEC, who did, he did strong support for optimizing FAB and FFX, NEC or Tsubasa. And of course, many industry partners, we did a collaboration with many partners, more than maybe 100 companies, including Shipbuilding Center of Japan, Toyota Motors, and Hitachi Limited, and so forth. That's all what I have to talk here. Thank you very much for listening.
Thank you very much, Professor Kato.